Additive manufacturing is a blanket term used to describe a manufacturing process that adds layers on top of each other in order to create a final product. It is different from traditional manufacturing such as milling. For example, milling a complex part results in large material losses, but for additive manufacturing, the cost remains the same regardless of part complexity. 3D printers rely on their own form of coding. This is generated from a slicer program. As the name implies, the slicer program slices a CAD model into individual layers. There are many forms of additive manufacturing, but we would like to focus on the three most common and the materials commonly associated with each type. Fused deposition modeling is the most common form of 3D printing. It is used by both hobbyist and industry partners. The materials that FDM printers use are called filaments. Common filaments are PLA, ABS, polycarbonate, and nylon. FDM printers extrude a set amount of molten filament onto a heated bed to form the first layer. Following layers build on the previous layer. They are considered the cheapest form of additive manufacturing, with industrial quality printers coming in at around $3,000 to $30,000. Next on our list, we have stereolithography, SLA for short. Commonly called resin printers, SLA is once again used by hobbyists and in low-volume industry roles. They offer greater dimensional precision and worse durability than parts produced on an FDM printer. Resin printers, as the name would suggest, use a special resin that solidifies when hit with a UV laser. Large SLA printers and the resin they use are more expensive than FDM printers. Finally, direct metal laser sintering machines are the leading type of printers for industrial applications. They belong to the family of additive manufacturing known as selective laser sintering. DMLS machines are specialized to use metal powders for their printing material. Popular metals in the automotive and aerospace industry, such as stainless steel, aluminum, Inconel, and titanium, are all available to be printed using DMLS. A roller will deposit a thin layer of metal onto the build layer, and then a CO2 laser will melt the metal powder on contact to form a new layer. DMLS and SLS printers are the most expensive type of printer commonly used in the industry, but the high upfront costs are usually offset by the materials saved compared to traditional manufacturing.
Polymers are generally found as what we call filaments in the 3D printing world. They are mostly used in FDM style machines. 3D printing has changed the way that prototyping is conducted, especially with the still dropping price to entry for basic FDM style machines. With a quality machine only costing several $100s and the material needed to feed these machines only costing around $20 a kilogram. Everything from large-scale prototyping to hobby-style model making uses these filaments. These machines are used for applications where a part may be too complex or expensive to prototype or manufacture by other conventional means. These filaments used in these machines come in many different types and variations for any application or property the end consumer may need. One of the two most popular filaments in the industrial and hobbyist markets for simple FDM style 3D printing is commonly referred to as PLA filament. PLA is a very cheap material which makes it accessible to all consumers. With its high surface finish and reliability when coming off the print bed, this makes it a great choice for rapid prototyping applications. Due to its popularity, there is a lot to choose from when it comes to colors and special subtypes of PLA filaments that can include filament types that have other materials suspended in them such as metals to increase their mechanical strength and durability. PLA is also a biodegradable thermoplastic which makes it very easy to work with, and another reason that it is one of the most popular filament types on the market. The other before mentioned popular filament type used in the hobbyist and industrial markets is ABS. ABS is one of the most successful thermal engineering plastics on the market today, and is not only used for 3D printing applications, but also used for other means of manufacturing such as injection molding. With ABS, the user has some concerns due to warping issues of the material when used for 3D printing. This is easily fixed using a heated build plate and a temperature controlled area. Most hobby level machines come equipped with this capability. ABS is also a cheap and easily obtainable material and comes in a very wide range of colors for the end user. Other than the standard filaments such as ABS and PLA, there is a large range of specialty filaments out there on the market. They range anywhere from carbon fiber to wood-infused PLA. These filaments are generally tailor-picked for their specific application on the part or parts that they are being used for. Some of these materials include PETG, PET, carbon fiber, nylon, and TPU or NinjaFlex, which is a rubber type filament that's used for when parts need to be flexible.
Resin 3D printing is a process using liquid resin as a build material, which is made up of a combination of acrylic, methacrylic, or epoxy monomers. Then exposing it to UV radiation, these monomers turn into a solid polymer by quickly forming bonds. The models are built layer by layer, forming molecular bonds with the previous layers. When it comes to resin-based printing, there are two main types, which are stereolithography, or SLA, and digital light processing, or DLP. The DLP process is similar to the SLA process, but instead of using a mirror galvanometer, it uses micrometer-sized mirrors that project an entire layer and can control the point of UV radiation emission. The types of commercial resins used are extensive, with each main group being named after the industry it's used in, such as engineering, medical, or jewelry, while each type has subgroups like high temp, castable, rigid, durable, or elastic. A few advantages are it gives highly detailed prints, is typically faster than printing with other materials. Also, the curing process for resin prints creates stronger layer adhesion, which gives the prints more uniform strength. Unfortunately, resin printing is expensive, not just the materials, but the equipment as well. There currently isn't the ability for composite prints. Resin prints are limited to one type of material at a time. Another disadvantage is the post-production process, which can be messy and complicated. Resin printing has a wide range of applications in many industries such as engineering and product design, manufacturing, dental research and education, entertainment and model making, healthcare, and also audiology. Some possible future applications are energy storage, flexible electronics, bioelectronics, optometry, tissue engineering, regenerative medicine, cancer research, drug screening. Although a couple of these are interchangeable, it looks like medical industries will gain the most from resin 3D printing in the future. In recent years, there has been a boom in the use of 3D printed resins in the dental industry due to technological advances. The initial use was mainly for printing dental molds, but now is used for anything from surgical guides to permanent crowns. Just like other industries in the dental industry, the type of resins used vary depending on the final use. Most of the resins u- Most of the resins used in the dental industry have to meet strict standards approved by the FDA due to health concerns. So this includes anything that will be used permanently or temporarily, such as impression trays, crowns, or splints. Primarily, they need to be non-toxic, have low water absorption and solubility. After these conditions are met, they also need to be high strength and precise fitting with having a low tendency to age or discolor. Not actually being needed, but being highly preferred. Graphene reinforced resin is still in development, but it is intended to be used for bone structure scaffolds and bone tissue engineering. The weight percent of this composition consists of 37 weight percent triethylene glycol dimethacrylate, 62 weight percent polyurethane, and 1 weight percent of phenobis phosphine oxide. The flexural strength and modulus can reach 115 megapascals and 5.8 gigapascals respectively. This is very, very promising for the future of prosthetics because it will give patients a made-to-order experience when it comes to bone replacements. For this particular study, researchers printed jawbones with square architectures like the one pictured, as well as sternums with circle architectures for testing.
I'm now going to cover the various types of metal 3D printing that are available, and then take a deeper look into one of them to show its effects on material properties. So there's SLM, also known as SLS and DMLS. SLM stands for selective laser melting, and it deposits a thin layer of metal powder that is then melted into a solid film via the use of powerful lasers, which slowly accumulates into a finished product as new layers build upon the previous ones. This process uses a potentially hazardous metal powder that requires skilled technicians to run. SLM printers cost upwards of $1 million US. There's also EBM, or electron beam melting, which uses a similar process to SLM, but uses an electron beam rather than a laser to fuse the material. This results in a faster yet less accurate part than SLM processes. Next we have the direct energy deposition printers, or DED. There is powder DED, which involves blowing a powder around the work area to create deposit individual layers, and has a laser mounted in the tip to create them. Then there's wire DED, which contains a spool of material that is extruded and melted similar to what common FDM printers do with plastics. This allows for much higher volume applications, but is much less accurate. Moving on, we have binder jetting, which is relatively new to the industry, and involves thin layers of metal powder that are bonded by intermittent layers of polymer. This allows for much faster production, as multiple polymer depositing heads may be used, similar to a 2D printer. This also costs upwards of $1 million. Then there's BPE, or bound powder extrusion. It works very similar to a typical 3D printer, where the metal powder is actually suspended in the filament. It's much safer to handle than the others, and it's about a fifth of the cost. But it involves additional washing, sintering, and heat treatment steps, and the final parts will shrink from the initial size due to the filament burn-off. But it does yield fully metal parts. Okay, so now we're going to take a deeper look into SLM 3D printing, but first let's discuss its advantages and disadvantages. So the advantages are it can create much smaller layers, which equals higher precision parts, which helps manufacturers use fewer, yet more complex parts that can be made out of higher strength materials. The disadvantages are lengthy and costly production, and the requirement of hazardous material and highly skilled workers. SLM is the most mature and the most common technology in the industry. These parts can be very complex and enable geometries that would otherwise be impossible to machine or require many more parts. However, these parts must undergo an extensive heat treatment process after they are manufactured to make sure that they are less ductile or more ductile, and decreasing their brittlity. So there was a 2012 study by KU Leuven, which is a Belgian university, on the titanium aluminum vanadium alloy, also known as TI-64. It was studied in its sintered state after being additively manufactured, and was found to have a very high yield stress of around 1 gigapascal, but very low ductility of 10%, as shown in the graph here. The SLM material was compared to conventionally hot forged and mill annealed material in both mechanical properties and crystal grain structure. So the study went on to establish methods of increasing the material's toughness via heat treatment according to the material's TTT diagram shown on the top right of the screen here. The typically mill annealed TI-64 has alpha plates, which are recrystallized through a deformation process, which turns them into alpha grains, while the SLM process produced completely martensitic structure known as alpha prime. In the reference material seen in the picture C on the left, the BCC beta structure is suspended in the alpha matrix, which is HCP. This is the target structure for the 3D printed material to be strengthened to. And on the bottom right figure, you can see the effects of different cooling rates on the crystal structure after being heated to 780, 843, and 1015 degrees C respectively, followed by slow furnace cooling for all of them. And you can clearly see the difference in the grains. So some takeaways. The study narrowed down the heat treatment process so that the grain formation became less cooling rate dependent and that the material's properties could actually be improved from its 3D printed state. Other 3D printed metals have shown to exhibit improved properties over traditionally manufactured materials due to initial crystal structures and subsequent heat treatments. One further takeaway here is that complex geometries can be created out of stronger materials using these processes moving forward. So the current applications are drone manufacturing, aerospace, and plumbing, to name a few, and future applications include medical devices due to the easier production of biocompatible materials, prosthetics, and aerospace.
Perhaps the most exciting future for additive manufacturing is in the aerospace and automotive industries. A company called Relativity was founded in 2015, and they aim to reduce the number of parts in a rocket from over 100,000 to just over 1,000 individual parts. They have designed their own 3D printer, which they dubbed Stargate, and have developed their own materials in-house. The automotive industry is also beginning to look forward to increasing the number of additive manufacturing processes. At the moment, most 3D printing occurs during the prototyping phases, but industry leaders want to incorporate the cost savings from additive manufacturing into their final assemblies.